Okay, so I'm going to be discussing the Krebs cycle, and yeah, so write it out. Actually, we'll do it this way. So first off, what we need for this cycle, we need 1 acetyl CoA, we need oxygen, and we need water. And this cycle is going to occur inside of the mitochondrial matrix, and it happens after glycolysis and oxidation, or pyruvate oxidation, so it's the second step of cellular respiration. Alrighty, now for the fun part. So the first step of this reaction, we're going to have acetyl-CoA come in. So acetyl-CoA is going to come in and combine with a 4-carbon molecule oxaloacetate. So 1, 2, 3, 4. And we have acetyl 1, 2. And this forms the 4-carbon molecule citrate. Ooh, can't really see that very well. We'll use red. 6-carbon molecule citrate. So in this first step, we lose CoA. So the CoA, we don't lose it because we're going to reuse it again later, but the CoA is disattached from acetyl-CoA. Now, the second step, citrate, the now 6-carbon molecule, is going to undergo an isomerization reaction. So we'll write that somewhere. So isomerization reaction, and is going to turn into its isomer, isocitrate. So this turns into isocitrate. Isocitrate. Perfect. Now, isocitrate is going to undergo the first oxidation reaction of this process. It's going to undergo the first oxidation and form alpha ketoglutarate, 5-carbon molecule. 5. Isocitrate is also 6-carbon. 1, 2, 3, 4, 5, 6. So in this process, isocitrate's oxidized, and this reduces NAD into its reduced form, NADH plus. And the electron that is associated now with NADH has a high amount of potential chemical energy, which is going to be used, or it's going to be exploited in the electron transfer chain. And as you may have noticed, this becomes a 5-carbon molecule, and we lose CO2 as waste. So CO2 is lost. And this is the first oxidation reaction. The next step is almost identical, except with one little difference. So alpha ketoglutarate is now going to be oxidized. And another NAD molecule is going to be reduced to NADH. And we're going to lose another CO2 molecule. And except the only difference between this step and the last step was that this is going to produce a 4-carbon molecule called succinyl. But this succinyl is going to is going to join itself with the CoA molecule lost in the first step to form succinyl CoA. 4-carbon succinyl CoA. Perfect. Now, the next step is a pretty key step, because this is the first time that we're going to see substrate level phosphorylation happen. So, let's go do nuclear. So, we're going to lose the CoA, and this CoA is going to be replaced by a phosphate group. So let's do this. So we're going to show plus phosphate group. And this process is going to turn GDP into G3P, which is going to turn ATP into ATP. And this whole process is substrate level phosphorylation. So we'll write it here. Substrate level phosphorylation. So this is going to be the only time that we're actually going to directly make an ATP in this process. So we lose the CoA molecule, coenzyme A. An inorganic a phosphate group is added to succinyl, turning GDP into G3P, which turns ADP into ATP through substrate level phosphorylation. And the new molecule that you're left with is succinate. 1, 2, 3, 4. The next step is another oxidation reaction where succinate is oxidized to turn into fumarate. Ooh, that's on an angle, whatever. Fumarate. And fumarate is going to be reduced into, an FAD molecule is going to be, so AD is going to be reduced with 2 hydrogens to FADH2. And once again, this is another electron carrier with high energy potential. This is a 4-carbon molecule. So moving on to the next step. This step is a pretty straightforward step. Fumarate is going to interact with water. So plus water to turn into malate. 1, 2, 3, 4. And in the last step of this process, malate is going to be reduced, or is going to be oxidized, sorry. And our last NAD molecule is going to be reduced to NADH. And malate is going to return to oxaloacetate, so that another acetyl-CoA can re-enter the cycle and it can start over again. So that's the process. Now let's summarize this real quick. So to start off, we had 1 acetyl-CoA. So we're going to do acetyl-CoA. We had 3 NAD molecules. We had 1 FAD. We had a single ADP. And we had a phosphate group. And all of this turns into 2 carbon dioxides, which makes sense because we started off with a 4-carbon, added 2 carbons to create 6 carbons, and we end with another 4-carbon molecule. So 2 carbon dioxide molecules as waste plus 3 NADH molecules. And so 3 hydrogen carriers plus 1 FADH2, another electron carrier, plus 1 ATP molecule. So that's the only high energy molecule that's produced immediately. This process plus our acetyl-CoA, plus our CoA molecule. So CoA. And something that's important to note is that from glycolysis we have 2 pyruvate molecules. Thus, 2 acetyl-CoA molecules are produced from glycolysis. So this whole cycle is going to go through 2 times. So we'll do that 2 times. And if we want a easier summary, all of these products are going to be multiplied by 2. So our total yield is going to be 4 carbons dioxides, 6. So we'll do this. 4, 6, 2, 2, and 2. Those are the adjusted numbers for when it goes around twice. And a way to remember this, the steps at least, order of steps can be crap, I know so flippin' much. But something that I do is I kind of group the steps together. So in the first 2 steps, oxaloacetate is turned into isocitrate. So nothing really, we're not gaining anything from there. So the first 2 steps, no gain. The next two steps, we have two oxidation reactions. And we also lose two carbons. So -2. The next step, succinyl-CoA turns into succinyl-CoA turns into 6 and 8, which turns ADP into ATP. So 1 ATP. So I do a 1A. The next step, we have one more oxidation. So 1O. Oh, that should be 2O for two oxidations. And the next step after that, we have an addition of water to turn fumarate into malate. And after that, we have our last oxidation, which turns it back into oxaloacetate. So that is the Krebs cycle. And I think I've hit everything. I think that's everything. So the products that are formed in this are two carbon dioxide, 6 NADHs, two FADHs, 2 ATPs, 2 CoAs. And the whole purpose of this cycle is so that all the carbon that's present in glucose is oxidized and released as CO2. And then, although only some ATP was formed by the substrate level phosphorylation, most of the potential energy is captured through the formation of NADH and FADH2 molecules, making them available for exploitation in the electron transport chain. And that is my video for the Krebs cycle. Thank you.